On a clear night in autumn, when the air grows crisp and the sky darkens early, you can spot it without any equipment. No telescope required, no binoculars needed. Just your eyes, adapted over millions of years to gather photons from distant sources. Look toward the constellation Cassiopeia, then shift your gaze slightly to the side. There, hanging in the darkness like a faint smudge of cosmic fog, you will find it. That pale blur, barely visible against the backdrop of stars, is not a cloud. It is not atmospheric haze. It is another galaxy entirely. Ancient astronomers noticed this patch of light centuries ago. Persian astronomer Abd al-Rahman al-Sufi described it in the year 964, calling it a small cloud. Charles Messier, cataloguing celestial objects in the 1700s, listed it as Messier 31. But it was not until the 1920s that we understood what we were really seeing. Edwin Hubble, using the newly completed 100-inch telescope at Mount Wilson Observatory, resolved individual stars within that fuzzy patch. He proved, definitively, that this object lay far beyond our own galaxy. It was an island universe, a galaxy in its own right, separated from us by distances that challenged comprehension. The moment of that discovery changed everything. Before Hubble's observations, many astronomers believed the Milky Way constituted the entire universe. They thought those fuzzy patches of light scattered across the night sky were simply nebulae within our own galaxy, clouds of gas perhaps destined to form new stars. The idea that other galaxies existed, entire island universes, each containing billions of stars, seemed almost fantastical. But Hubble identified specific types of variable stars in Andromeda. Stars whose brightness changed in predictable patterns. By measuring these variations, he could calculate their true luminosity, and from that, their distance. The numbers were staggering. Andromeda lay nearly 1 million light-years away, far beyond anything previously measured. That faint smudge holds 1 trillion stars, each one a sun in its own right, many of them larger and brighter than our own. It contains billions of worlds that could support life, rocky planets orbiting in habitable zones where liquid water might pool on their surfaces, and perhaps, just perhaps, it harbours millions of civilizations at this very moment, beings made of matter and energy like us, looking up at their own night skies and asking themselves the same question humans have pondered since we first gained consciousness. Is anyone else out there? It sits as our closest major neighbour among the galaxies, a spiral system much like our own Milky Way, spinning slowly through the void. And yet, despite this cosmic proximity, despite being our nearest galactic companion, we will never reach it. Not in 1,000 years, not in 1 million, not in 1 billion. The fundamental rules of physics have built an invisible barrier around humanity. A cage constructed not of metal or energy, but of distance and time itself. This barrier is so enormous and so complete that even if you could somehow travel at the speed of light itself, the fastest velocity possible in our universe, you would still need 2.5 million years to cross the distance between here and there. But that is not even the most troubling part of this cosmic isolation. The sheer distance, while staggering, represents only the most obvious obstacle. The true reason we cannot get to Andromeda is far more unsettling than simple distance, far more profound than mere numbers. It challenges everything we believed about travel, about time, about causality, and about the very fabric of reality. It forces us to confront uncomfortable truths about our place in the cosmos, truths that most people would rather not consider too deeply. If you appreciate this kind of cosmic journey, If you find yourself drawn to these contemplations of scale and isolation and meaning, consider liking and subscribing. It truly helps us continue creating this content, allows us to keep exploring these vast questions together. Now, settle in and get comfortable. Perhaps dim the lights around you. Let the everyday world fade slightly into the background. Let us begin this journey together, even if it is a journey we can only take in our minds. 1 trillion stars, 1,000 billion individual points of light, each one a nuclear furnace fusing hydrogen into helium, each one pouring energy into the void around it. The human mind struggles with numbers this large. We simply lack the cognitive architecture to truly comprehend such quantities in any meaningful way. Our brains evolved to understand small numbers, the kind you could count on your fingers or toes, the number of people in your family or tribe, the number of days until the next full moon. Andromeda is actually slightly larger than our Milky Way, spanning roughly 220,000 light-years from edge to edge. Its spiral arms wind gracefully outward from a dense central bulge, glowing with the light of ancient red stars. Newer, bluer stars trace the spiral patterns where gas clouds collapse and ignite. The galaxy rotates, though so slowly that we will never see the motion directly. It takes about 250 million years for Andromeda to complete one full rotation. The last time it was in its current orientation, dinosaurs had not yet evolved on Earth. Within Andromeda's structure lie multiple distinct regions. The central bulge contains older stars formed billions of years ago when the galaxy was young. These stars orbit in random directions, creating a spherical swarm at the galaxy's heart. The disk, by contrast, hosts younger stars, gas, and dust, all orbiting in roughly the same plane. And surrounding everything, extending far beyond the visible edges, lies a massive dark matter halo. This invisible mass, detectable only through its gravitational effects, outweighs all the visible matter in the galaxy by a factor of 10 or more. We cannot see it, cannot touch it, can only infer its presence from how it shapes the orbits of stars and gas clouds. To put this in perspective, consider that every star in Andromeda could have its own planetary system. Not all of them do, but many will. If even a small fraction, say 10%, host planets, that gives us 100 billion planetary systems. If each system averages just 3 planets, we are looking at 300 billion worlds. Some will be gas giants like Jupiter, others will be ice worlds like Neptune, but among them billions will be rocky planets like Earth, orbiting at distances where temperatures allow liquid water. The sheer abundance of potential is staggering. Each of those worlds has its own geology, its own weather patterns if it has an atmosphere, its own unique history spanning billions of years. Some may have oceans covering most of their surface. Others might be desert worlds with rare pockets of water. A few might have conditions remarkably similar to Earth, with continents and seas and seasonal variations. And on some unknown fraction of these worlds, life might have emerged just as it did here. Consider the statistical probability. If even 1 in a million of those rocky planets developed life, that would still be thousands of living worlds. If 1 in 1,000 of those living worlds developed intelligent life capable of technology and civilization, we would still be talking about multiple civilizations potentially existing in Andromeda right now. They might be looking at our galaxy through their own telescopes, wondering if anyone is looking back. They might be having this exact same conversation about the impossibility of reaching us, feeling the same cosmic loneliness, confronting the same vast distances that separate island universes. If you began counting the stars in Andromeda at 1 per second, maintaining a steady rhythm like a heartbeat, never pausing to sleep, eat, breathe, or rest, never stopping for any reason at all, you would finish after 31,700 years. Think about that duration for a moment. You would need to start your count back during the last ice age, when vast glaciers covered much of the northern hemisphere and sea levels sat hundreds of feet lower than today, when woolly mammoths walked across frozen landscapes and saber-toothed cats prowled through ice age forests. You would just be beginning your count. When humans had not yet discovered farming, when we still lived as nomadic hunter-gatherers, following herds of animals and seasonal patterns of plant growth, you would still be counting. You would count through the emergence of ancient Mesopotamia, the first cities rising from the plains between the Tigris and Euphrates rivers. You would count through the construction of the pyramids at Giza, those massive stone monuments built by thousands of workers over decades. You would count through the rise and fall of ancient Egypt, through the glory days of Greece and Rome, through the collapse of Rome and the darkness that followed in Europe. You would count through the Renaissance, when art and science flowered again in Italy and spread across the continent. You would count through the Industrial Age, when steam engines and factories transformed human civilization. You would count through 2 global conflicts that reshaped the political landscape of Earth. You would count through the beginning of space exploration, when humans first left their home planet and set foot on another world. You would count through countless generations still to come, generations not yet born, perhaps not even conceived. And even then, even after all that time and all that history, you would not be done counting. Every single one of those trillion stars represents a potential story. Most are probably lonely suns with no planets at all, or perhaps just barren rocks and gas giants in unsuitable orbits. But statistical probability alone guarantees that millions, perhaps billions, have conditions that could support some form of life. Right now, at this very moment, somewhere among those trillion suns, a planet might be experiencing its first sunrise after a long night. Somewhere, waves might be crashing on an alien shore. Somewhere, something might be taking its first breath of an alien atmosphere, beginning a journey that could, over billions of years, lead to intelligence and technology and the same questions we are asking. The light you observe when you look at Andromeda tonight, those photons striking your retina and creating the sensation of seeing something distant and faint, began its journey 2.5 million years ago. Let that sink in for a moment. 2.5 million years ago, when our early ancestors had not yet mastered the use of fire, when our hominid relatives were still learning to knap stone tools, still discovering that certain rocks could be fractured in ways that created sharp edges useful for cutting meat and scraping hides, when the human brain was still millions of years from developing speech or creating art or possessing the ability to wonder about faraway galaxies, when consciousness itself, at least in its human form, was still emerging from more primitive neural structures. Those ancient particles of light, photons created in the atmospheres of stars in Andromeda, have been moving through the cosmic emptiness ever since. They have been travelling across a void so immense, so utterly empty, that our language lacks adequate words to capture it. For 2.5 million years, these photons have crossed the intergalactic gulf. They passed through regions of space containing essentially nothing, no matter to interact with, no forces to deflect them, just pure emptiness, stretching in all directions. They witnessed, in a sense, the expansion of the universe itself, the gradual stretching of space that carried their origin point farther away, even as they raced toward their destination. They crossed the boundary into our galaxy perhaps 50,000 years ago, entering the disk of the Milky Way and beginning their passage through our local stellar neighborhood. During their journey through our galaxy, these photons passed by countless stars. each one a potential sun for its own system of worlds. They travelled through nebulae, those vast clouds of gas and dust where new stars are born. They crossed the spiral arms of the Milky Way, dense regions where star formation occurs most actively. They navigated through relatively empty regions between the arms, where stars are scattered more thinly. All of this happened while humans were still primitive hominids, while our brains were still evolving, while our future as a technological species remained utterly uncertain. Think about what was happening on Earth during that photon journey. When those particles of light left Andromeda, the creatures that would eventually become humans were small, ape-like beings in Africa. They had no language, no art, no tools, beyond perhaps the most primitive stones picked up and used without modification. The entire story of human development, from those primitive ancestors to modern civilization, occurred while photons from Andromeda travelled through space toward us. Every innovation, every discovery, every step forward happened during their flight. The discovery of fire occurred while they travelled. The development of language occurred while they travelled. The invention of agriculture, the building of the first cities, the creation of writing, the development of mathematics, the understanding of astronomy itself, all of it happened during their journey. And yet, from the photon's perspective, travelling at light speed, no time passed at all. This is the strange nature of relativity. For a photon, its emission and absorption happen in the same instant. It experiences no journey, no passage of time. Only we, the observers, experience the wait. And finally, tonight, some tiny fraction of these ancient photons, survivors of a journey beyond human comprehension, happen to strike the light-sensitive cells in the back of your eye. They complete their journey in your consciousness, bringing you information about a place so distant that the very concept of distance begins to lose meaning. You are seeing Andromeda not as it is tonight, but as it was when your ancestors were barely recognizable as human, when the entire story of human civilization lay in an inconceivable future. Interestingly, Andromeda and the Milky Way are not destined to remain separated forever. Gravity, that patient and relentless force, is slowly drawing us together. In about 4 billion years, these two great spiral galaxies will collide. The word collision is slightly misleading, however. Galaxies are mostly empty space. The distances between stars are so vast that when two galaxies merge, stars rarely, if ever, collide with each other. Instead, they pass by like ships in the night, their mutual gravity stirring both galaxies into new configurations. The collision will take place over hundreds of millions of years. First, the outer edges of the galaxies will begin to interact, gravitational forces pulling streams of stars out in long tidal tails. The spiral structure of both galaxies will become distorted, then gradually destroyed. Eventually, after multiple passes where the two galaxy cores swing around each other, they will settle into a single massive elliptical galaxy. Astronomers have already given this future merged galaxy a name: Milkomeda, or sometimes Milkdromeda. By the time this merger completes, our Sun will be nearing the end of its life. It will have already expanded into a red giant, possibly engulfing Earth entirely, definitely making our planet uninhabitable. If any form of human civilization survives to witness the merger, it will need to have migrated to other star systems long before. Those descendants, if they exist, will live in a very different galaxy than the one we inhabit today. The organized spiral structure will be gone, replaced by the chaotic elliptical shape of a merged galaxy. During the merger, our solar system will likely be flung into a new orbit, possibly ejected toward the outer reaches of the combined galaxy, or thrown inward toward the crowded center. The night sky will transform dramatically. instead of a faint band of the Milky Way arcing overhead. Observers will see a sky crowded with stars from both galaxies. The center of the merged galaxy will glow intensely, a massive concentration of stars packed into a relatively small volume. But even then, even witnessing this cosmic collision from within, traveling between the two original galaxies will remain impossible. The distances within a single galaxy are already too vast for human travel, let alone crossing between two merging ones. This distance defies our ability to understand it in ways that should unsettle anyone who thinks about it deeply, anyone who really tries to grasp what these numbers mean. Our minds evolved to comprehend distances we could walk in a day, or maybe travel in a few weeks. We developed instincts for spaces we could cross on foot, landscapes we could survey with our eyes from a hilltop or tall tree, horizons we could reach before the sun went down and darkness made travel dangerous. The open plains of East Africa that shaped human thinking, that created the basic cognitive architecture we still use today, measured perhaps 100 miles in any direction. This was the scale of reality for our ancestors, the complete universe as far as they were concerned. Our ancestors needed to know where dangerous animals might hide, where they could find reliable water sources, where fruit trees were growing, and when they would bear fruit. They needed to understand the landscape on a practical, survival level. They needed to remember the location of waterholes that only filled during certain seasons. They needed to track the movements of herds across familiar territories. They needed to recognize landmarks that would guide them back to camp before darkness fell. Distance for them meant something concrete and personal. A 2-day walk to find better hunting grounds. A half-day journey to reach a known water source. These were the scales that mattered for survival, the distances their brains learned to process intuitively. Nothing in our evolutionary past equipped us to understand distances measured in millions of light years. Nothing prepared us for scales where the speed of light itself becomes a meaningful constraint. We are using Stone Age brains, cognitive tools, shaped for finding food and avoiding predators, to contemplate distances that dwarf entire galaxies. It is like trying to understand quantum mechanics using only your sense of touch, or trying to perceive colours using only your sense of hearing. The tools do not match the task. Let me attempt to make this understandable, though I should warn you from the outset, the effort may only increase your sense of cosmic disorientation. The very act of trying to comprehend these scales might leave you feeling smaller and more isolated than before. But perhaps there is value in that feeling, in confronting our true cosmic situation honestly rather than hiding behind comfortable abstractions. A single light year measures roughly 6 trillion miles. If you write that number out in full, with all its zeros carefully lined up, it looks like this: 6 million miles. 6 followed by 12 zeros. Try to visualize that number. Try to feel its weight. You cannot, not really. The number is too large, too far beyond human experience. We can write it, we can calculate with it, but we cannot truly comprehend it in any intuitive sense. Let me try another approach. Imagine you could fold space somehow, compress distance like folding a piece of paper. Even if you could fold the distance to Andromeda in half, you would still be looking at over 1 million light years. Fold it in half again, still over 500,000 light years. You would need to fold it 20 times, reducing the distance by a factor of more than 1 million before you reach the distance to our nearest star. The scale is so vast that even massive reductions barely make a dent. Light itself, the fastest phenomenon in the universe, the absolute speed boundary set by the laws of physics, needs an entire year to cover this distance. Light which moves so fast that it appears instantaneous over any distance we experience in daily life. Light which crosses a room in billionths of a second, which could circle Earth's equator more than 7 times between one heartbeat and the next. Light, travelling at 186,000 miles per second, still requires 12 full months to traverse a single light year. Think about what this means for communication. If we somehow manage to send a radio message to Andromeda, travelling at the speed of light, like all electromagnetic radiation, that message would take 2.5 million years to arrive. Any response would take another 2.5 million years to return. A simple exchange, a question and answer, would span 5 million years. Entire geological epochs would pass between transmission and reply. Continental plates would drift thousands of miles. Ice ages would come and go. Species would evolve and go extinct. By the time you received an answer to your message, assuming anyone was there to answer, your civilization would almost certainly no longer exist. Imagine sending a message asking a simple question: what is your world like? By the time that question arrives, whatever civilization receives it might be unrecognizably different from what it was when the message was sent. Their technology will have advanced or declined. Their society will have transformed. Their very biology might have changed through natural evolution or genetic engineering. They might not even speak the same language anymore, might not share the same values or interests. And then imagine waiting for their reply. 5 million years total for a single exchange. Your species would likely be extinct by then, replaced by descendants so different they would constitute an entirely new species. The continents on your planet would have moved hundreds of miles from their current positions. Your sun would have moved through space, carrying your solar system to a different location in the galaxy. The night sky would look different, stars rearranged by their individual motions through space. Everything you knew would be gone, transformed beyond recognition by the time you heard back. A beam of light can circle our planet 7 times in 1 second. Think about that for a moment. In the time it takes you to say the word one, light could wrap around the entire circumference of Earth 7 complete times. It can travel from Earth to the Moon in just over 1 second, covering the roughly 240,000 miles of empty space between them, faster than you can snap your fingers twice. It crosses the space between Earth and the Sun in approximately 8 minutes, racing across 93 million miles of void at a speed that human brains cannot really process. When you look at the Sun, you are seeing it not as it is in this precise moment, but as it was 8 minutes ago. If the Sun were to suddenly vanish, wink out of existence for some impossible reason, we would not know it for 8 full minutes. The light from the Sun's surface, the last photons it emitted before vanishing, would continue their journey toward us, and we would continue seeing the Sun as normal until those final photons arrived and darkness fell. This 8-minute delay creates strange scenarios if you think about them carefully. When you see a solar flare on the Sun's surface, you are watching an event that already finished 8 minutes ago. When scientists monitor solar activity to predict space weather that might affect Earth, they are looking at the past, trying to forecast present conditions based on information that is already 8 minutes out of date. By the time we see a dangerous solar event beginning, charged particles might already be well on their way to Earth. Yet even moving at this staggering speed, this velocity that makes a mockery of every speed we experience in human life, light requires a full year to cross just 1 light year of cosmic space. A full year of continuous travel at maximum possible velocity, and you have covered just 1 unit of cosmic distance, the basic measuring stick astronomers use for the nearby universe. Our closest star beyond the Sun, Proxima Centauri, lies 4.2 light years away. This small red star a dim dwarf that burns its nuclear fuel slowly and will outlive our sun by trillions of years, represents the nearest possible target beyond our solar system. If you wanted to visit another star, any other star at all, Proxima Centauri is the closest option available. There is nothing nearer. The gap between our Sun and Proxima Centauri represents the minimum distance you would need to cross to reach any stellar destination. Proxima Centauri is so dim that you cannot see it with the naked eye, despite being our closest stellar neighbour. It is a red dwarf, cool and small, with less than 1/8 the mass of our Sunday. Its total light output is less than 2% of what our Sun produces. If you replaced our Sun with Proxima Centauri, Earth would freeze into a solid ball of ice almost immediately. Any habitable worlds around Proxima Centauri would need to orbit very close to the star. So close that they would likely become tidally locked, always showing the same face to their sun, one side in permanent daylight, the other in eternal darkness. Using the fastest spacecraft humans have ever constructed, a probe designed to use the sun's gravity to accelerate to maximum velocity, reaching Proxima Centauri would take more than 70,000 years. 70,000 years of continuous flight through the void. 70,000 years during which the spacecraft would need to function perfectly without any maintenance or repairs. 70,000 years during which no human aboard could possibly survive to see the destination. 70,000 years ago, modern humans were just starting to move out of Africa, spreading into the Middle East, and beginning the long migration that would eventually carry our species to every continent on Earth. The complete story of human civilization, every empire that rose and crumbled, every conflict that occurred, every book ever composed, every song ever performed, every thought any human ever had about art or science or meaning, all of it would fit many times over into the travel time to our nearest stellar neighbour. You could replay the entire history of human civilization from the first permanent settlements to the present day, and you would still have tens of thousands of years of travel time remaining. During that 70,000-year journey, the spacecraft would drift through the space between stars in complete isolation. No landmarks to navigate by, no sense of progress except perhaps the slow brightening of Proxima Centauri ahead and the slow dimming of the sun behind. The cosmic background would barely change. The constellations would shift slightly, but stars are so distant that even travelling for thousands of years produces only small changes in their apparent positions. For generation after generation aboard that ship, nothing would change. The view would remain essentially static, a frozen tableau of stars that shifts too slowly for human lifetimes to perceive. Now multiply that distance by 600,000. Multiply it by a number so large that it loses concrete meaning. Andromeda sits 2.5 million light-years from Earth. Written out completely, without scientific notation or abbreviations, this distance equals 15 million trillion miles. That is, 15 followed by 18 zeros. 15 quintillion miles, if you want to use the proper name for a number that large, though giving it a name does nothing to make it comprehensible. If you could somehow drive a car at normal highway speeds toward Andromeda, travelling at a steady 60 miles per hour, never stopping for fuel, rest or repairs, never slowing down for any reason, the trip would require 40 trillion years. Let me put that in perspective. The universe itself, all of space and time and matter and energy, has only existed for 13.8 billion years. That is the age of reality itself. Measured from the Big Bang to the present moment, you would need to travel for nearly 3,000 times longer than the entire age of the cosmos just to arrive at our nearest major galactic neighbour. You would need to live through 3,000 complete life cycles of the universe, 3,000 iterations from the Big Bang to the present, just to drive a car from here to there. The absurdity of this comparison almost makes it meaningless. Almost, but not quite. It still tells us something important about the scale of intergalactic space. At 60 miles per hour, you cover 1 mile every minute. At that rate, you could drive across the United States in about 2 days of continuous travel. You could drive around the entire Earth in about 2 weeks. You could drive to the moon in about 6 months if there were a road. These are at least comprehensible timescales, durations we can relate to human experience. But 40 trillion years? That number exists in a realm beyond human understanding, beyond even geological or astronomical timescales we are familiar with. But raw numbers, regardless of how many zeros they contain, regardless of how carefully we line them up or how many different ways we write them, cannot truly convey the overwhelming nature of this distance. They slip away from the human mind like water on glass, too vast to grip with our evolved understanding. Our brains simply did not develop the capacity to internalize these quantities. We can manipulate them mathematically, we can write equations and solve problems, but we cannot feel them in any meaningful way. Perhaps we need to consider whether any theoretical physics might offer a way around these distance problems. Science fiction has popularized concepts like wormholes, theoretical shortcuts through space-time that might allow travel between distant points without crossing the space in between. The mathematics of general relativity does indeed allow for such structures. Einstein's equations do not forbid them, but this represents mathematical possibility, not physical reality. Creating a traversable wormhole, one that a spacecraft or even information could pass through, would require exotic matter with negative energy density. This is not matter as we know it, not atoms or molecules or any substance we have ever encountered. It would need to have properties that actively push against space-time itself, creating the opposite effect of normal matter and energy. We have never observed such material. We have no idea how to create it. Most physicists suspect it cannot exist at all, that quantum mechanics or other physical principles we have not yet fully understood will forbid its existence. Even if exotic matter could somehow exist, creating a wormhole would require manipulating it in quantities comparable to the mass of stars. You would need to gather stellar masses of this impossible substance and arrange it in precise configurations to open and stabilize a wormhole mouth. The energy requirements would dwarf even those needed for conventional relativistic travel, and you would still face the problem of where the other end of the wormhole would be. You cannot create a wormhole to Andromeda unless you can first get to Andromeda to position the other mouth. The wormhole offers no shortcut for the initial journey. Some theorists have proposed that naturally occurring wormholes might exist, left over from the Big Bang, or created by exotic quantum processes. But even if such structures exist, they would almost certainly be microscopic, far too small for anything larger than subatomic particles to traverse. And they would likely be catastrophically unstable, existing for tiny fractions of a second before collapsing. The idea of finding a naturally occurring, stable, traversable wormhole that happens to connect Earth to Andromeda stretches credulity beyond any reasonable limit. Other speculative ideas include Alcubierre drives, theoretical devices that would warp space-time around a spacecraft, allowing it to effectively move faster than light without actually traveling through space faster than light. Again, the mathematics of general relativity allows for such configurations, but again, they would require exotic matter with negative energy density, along with energy inputs that might require converting significant fractions of planetary mass into pure energy. These concepts remain firmly in the realm of speculation, with no clear path from theoretical possibility to practical implementation. The fundamental problem remains the same across all these speculative solutions. The physics that creates the barrier also makes the theoretical workarounds either impossible or so fantastically difficult that they might as well be impossible. You cannot cheat the universe. The rules are the rules, and distance, combined with the speed of light limit, creates an effective barrier that no clever physics is likely to circumvent. Let me try a different way to explain this, a method that might bypass the number problem and appeal to spatial intuition instead. Imagine reducing the entire solar system, all the planets and moons and asteroids and comets orbiting our sun, until the sun itself becomes a basketball sitting at the center of a gymnasium. Picture this in your mind. A standard basketball, about 9 inches in diameter, sitting on the polished wooden floor of a gym. That basketball represents the sun, a star containing 99.8% of all mass in our solar system. A ball of plasma so massive that its gravity holds entire worlds in orbital paths. On this scale, where we have shrunk the sun down to something you could hold in your hands, Earth would shrink to a grain of sand orbiting about 26 feet from that basketball. Not a pebble, not a marble, but a grain of sand. A single, tiny grain like you might find on a beach or in an hourglass. That grain of sand, smaller than the period at the end of this sentence, contains everything humanity has ever experienced. Every person who ever existed, every city ever constructed, every war ever fought, every love story ever lived, every aspiration ever pursued, every thought any human ever had, all of human history, all of human emotion, all of human achievement and failure and hope and despair, all of it compressed into that single grain of sand orbiting a basketball in a gymnasium. The scale of this reduction should be humbling. It should make you feel small in a way that is uncomfortable but important. We are so tiny, so utterly insignificant in spatial terms, that on this scale, where we have shrunk the solar system to fit in a gym, all of human experience becomes invisible to the naked eye. Every great moment in human history, every tragedy, every triumph, every ordinary day, lived by billions of people across thousands of years, all of it fits on a speck so small you could barely see it without magnification. The construction of the Great Wall of China, visible from space in our actual scale, would be completely invisible on this grain of sand. The pyramids of Egypt, massive monuments that have stood for thousands of years, would be smaller than a single atom. All of human civilization compressed to subatomic scales. Jupiter, the largest planet in our solar system, the gas giant with a mass greater than all other planets combined, would become a marble on this scale. A standard glass marble, perhaps half an inch across, positioned 130 feet from the basketball sundae. Already we are leaving the gymnasium. Jupiter sits across the parking lot. And Jupiter is massive, so large that you could fit more than 1,000 Earths inside it, so massive that it generates its own heat through gravitational compression, almost but not quite massive enough to ignite nuclear fusion and become a star itself. Saturn, with its spectacular ring system, would be a slightly smaller marble sitting about 230 feet away. Those magnificent rings, so prominent in telescope images, so distinctive that they make Saturn instantly recognizable, would be thinner than a sheet of paper on this scale, barely visible even if you looked closely. The rings are made of countless billions of ice particles, each one orbiting Saturn independently. But their total thickness averages only about 30 feet, despite stretching hundreds of thousands of miles in diameter. On our basketball scale, they would be impossibly thin, like trying to see a single layer of molecules. Uranus and Neptune, those ice giants at the outer reaches of our solar system, would be small marbles sitting even farther out. Neptune, the farthest major planet, that frozen realm of violent winds and methane oceans, that blue world where supersonic storms rage in an atmosphere of hydrogen and helium, would sit roughly half a mile from the gymnasium, half a mile through suburban streets or across fields, depending on where this imaginary gymnasium sits. Beyond Neptune, the Kuiper Belt would extend for another mile or two, a region of icy debris left over from the solar system's formation. Small icy bodies, including dwarf planets like Pluto, orbit in this distant realm. On our scale, they would be grains of sand scattered across miles of empty space, so far from the basketball sun that sunlight barely warms them. And beyond even the Kuiper Belt lies the Oort cloud, a spherical shell of comets surrounding our solar system at distances up to 2 light-years away. On our basketball scale, the Oort cloud would extend almost all the way to Australia. At this same scale, where our entire solar system fits inside a small neighbourhood, where the sun becomes something you could hold in your hands and Earth becomes invisible to the naked eye, where would the closest star be? Where would we find Proxima Centauri, our nearest stellar neighbour? Another basketball, identical to the one sitting in the gymnasium, located in Australia. If you stood in New York, holding the basketball sun, looking across the parking lot at the marble Jupiter, glancing down the street at distant Neptune, the nearest other star would be another basketball sitting in Sydney, 12,000 miles away across the entire North American continent and the Pacific Ocean. Think about that gap for a moment. The space between those two basketballs would hold essentially nothing at all. No matter, no light, no sound, no planets, no asteroids, no comets, just emptiness extending across continents and oceans at a scale where our entire solar system, the complete cosmic neighbourhood we call home, fits inside a single building. All the space missions humans have ever launched, all the probes and satellites and space stations, all of them have explored less than the distance from the basketball sun to the marble Jupiter. We have barely left the gymnasium. Voyager 1, the most distant human-made object, launched in 1977 and still travelling, has reached a distance of about 14 billion miles from Earth. That sounds impressive until you put it in our basketball scale. Voyager 1 has travelled about 3/4 of a mile from the gymnasium. It has not yet left the neighbourhood. It will take another 30,000 years before it passes even remotely close to another star, and even then it will miss by trillions of miles. The emptiness between stars is so vast that even travelling for tens of thousands of years barely begins to cross it. And Andromeda? At this scale, where stars become basketballs separated by oceans, where our solar system shrinks to the size of a gymnasium, where Earth becomes a grain of sand and human civilization becomes microscopic, the Andromeda Galaxy would sit beyond the orbit of Mars, around the actual Sunday. Not the scale model sun, but the real Sunday. We have shrunk our cosmic neighbourhood by factors that dwarf human imagination. We have compressed space until stars become handheld objects, and Andromeda still ends up more than 50 million miles away. The nearest major galaxy to our own lies so incredibly distant that even at scales where stars become objects you could hold, where entire solar systems fit inside buildings, the gap between us remains astronomical. The word astronomical, in fact, barely does it justice. We need new vocabulary for this kind of distance, new concepts that our current language cannot express. The emptiness between galaxies surpasses anything most people have ever considered, anything humans typically encounter in their thoughts about space. When people think about the vacuum of space, they usually imagine the space between planets, or perhaps the space between stars. But intergalactic space represents a different category of emptiness entirely, a void so extreme it approaches the theoretical limits of nothing. Intergalactic space contains roughly 1 atom per cubic meter. Picture a cube with sides 1 meter long, about the size of a small closet. Inside that entire volume, on average, you would find 1 single hydrogen atom, 1 lone proton with 1 electron orbiting it, separated from its nearest atomic neighbours by distances vast even on the atomic scale. That atom floats alone in a space large enough to hold your body, drifting in emptiness, rarely, if ever, interacting with anything else. That single atom in a cubic meter might seem like true emptiness, but consider what emptiness really means. That atom has mass, position, velocity. It represents something rather than nothing. Yet, in intergalactic space, that single atom in a cubic meter represents the average. Some regions might contain 2 or 3 atoms per cubic meter. Other regions might contain none at all for cubic meters on end. The distribution is not uniform but varies randomly, creating a kind of texture to the emptiness, regions slightly more empty and slightly less empty than average. Compare this to the atmosphere on Earth, the air you are breathing right now as you read or listen to these words. The atmosphere at sea level contains about 25 trillion molecules per cubic meter. That is 25 followed by 24 zeros. 25 septillion molecules in the same volume that holds just 1 atom in intergalactic space. The air you are breathing right now contains more particles in a single breath in the lungful you just inhaled than you would encounter in cubic miles of intergalactic void. Think about that ratio. The air around you is 25 trillion times denser than intergalactic space. That is not a difference in degree, but a difference in kind. It is like comparing the population density of Manhattan at rush hour to having 1 person scattered across an area larger than North America. Actually, that comparison is nowhere near extreme enough. The difference between Earth's atmosphere and intergalactic space is so vast that we lack everyday comparisons to capture it. Intergalactic space approaches the theoretical limit of emptiness possible in our universe. Even the quantum vacuum, the so-called empty space at the smallest scales, seethes with virtual particles popping in and out of existence. But the average density of matter in intergalactic space comes so close to absolute zero that the distinction almost does not matter. Even the most advanced vacuum chambers humans can build on Earth, chambers where we pump out nearly all the air and seal them against any leaks, contain trillions more particles than the average cubic meter of space between galaxies. The void, separating the Milky Way and Andromeda, represents an emptiness more extreme than any human technology can produce. We can create vacuums in laboratories, we can pump chambers down to incredibly low pressures, but we cannot replicate the sheer emptiness of intergalactic space. The void between galaxies stands as the best vacuum in the known universe. A vacuum so perfect, it serves as a practical definition of nothing. This void extends for 2 million light years, with essentially nothing throughout. No stars to use for refueling, no planets to land upon for rest or repairs, no matter to interact with, no cosmic way station where exhausted travellers might stop to fix their vessels or gather supplies. Just absolute emptiness reaching in every direction for distances that dwarf not only human imagination, but human existence itself. The emptiness is not just large, it is so large that large becomes an inadequate word. It is so empty that empty becomes an understatement. To cross this void, you would travel through darkness, more complete than any darkness experienced on Earth. Even the darkest cave, the deepest ocean trench, still contains matter around you. The darkness is created by absence of light, but matter still surrounds you. In intergalactic space, you would have true isolation. No ground beneath you, no sky above you, no landmarks in any direction, just stars in the far distance, too far away to provide any sense of place or orientation. You would be floating in an infinite void, with nothing to indicate motion or position except the slow drift of distant galaxies. Scientists have identified approximately 50 small dwarf galaxies orbiting in the space between us and Andromeda. Like cosmic stepping stones scattered across the void, these tiny galactic systems hold millions or billions of stars each. They are true galaxies in their own right, massive collections of stars and gas and dark matter, but compared to the Milky Way or Andromeda they are tiny, small points of light in the intergalactic darkness, barely visible even with powerful telescopes. These dwarf galaxies have their own stories, their own histories spanning billions of years. Some are ancient, formed in the early universe when galaxies were first beginning to assemble. Others might be relatively young, perhaps torn from larger galaxies by gravitational interactions. Each one represents a complete stellar system with potentially millions of planets, perhaps even harboring life, isolated in the void between major galaxies. If intelligent beings arose in these dwarf galaxies, they would find themselves in an even more isolated situation than we face, separated from both the Milky Way and Andromeda by hundreds of thousands of light years. Imagine being born on a planet in one of these dwarf galaxies. When you looked up at your night sky, you would see far fewer stars than we see. Your entire galaxy might contain only a few million stars instead of hundreds of billions. The night sky would be sparse, dim, with large regions of darkness between scattered stars. And in the distance, if your eyes were sensitive enough, you might see two faint smudges of light, the Milky Way and Andromeda, your nearest major galactic neighbours, both impossibly far away, both utterly unreachable. But even these intermediate galaxies lie hundreds of thousands of light years apart from each other. They offer no real path, no practical route through the void. They are not stepping stones in any meaningful sense. You cannot hop from one to the next. They simply represent occasional reminders that some matter exists in what is otherwise nearly perfect. Vacuum, small islands of matter in an ocean of nothing. The journey to Andromeda would cross this void for the entire distance. Every mile of the trip, every inch, every microscopic fraction of movement would occur in this extreme emptiness. Imagine launching a spacecraft capable of travelling at 1/10 the speed of light, a velocity that would seem utterly miraculous given our current technology, a speed that would require breakthroughs in physics and engineering that we cannot currently imagine. At this extraordinary speed, you would still need 25 million years to reach Andromeda. 25 million years of continuous travel through perfect vacuum. 25 million years during which nothing would change outside your windows except the slow drift of stars and the gradual approach of your destination. 25 million years ago, our most recent ape ancestors were just beginning to evolve in Africa. The entire lineage, from those early primates to modern humans, the complete story of human evolution, from tree-dwelling apes to beings capable of contemplating the cosmos, would unfold in less time than a single crossing to Andromeda. The human species would rise, flourish, build civilizations, develop language and art and science and philosophy, reach for the stars and likely go extinct, all long before any ship completed the journey. Your species would not survive long enough to see your destination. In cosmic terms, humans represent a flash, a brief moment of awareness in a universe that thinks in timescales we cannot grasp. But perhaps we could travel faster. Perhaps some breakthrough in physics, some discovery we have not yet made, might allow us to approach the speed of light itself. Let us imagine, just for the sake of argument, a spacecraft travelling at 99% of light speed. At this velocity, relativistic effects would begin to transform the nature of the journey in ways that seem almost magical, but are in fact just the normal behaviour of space and time at extreme velocities. Time would slow for the travellers relative to Earth. This is not a trick or an illusion, but a fundamental property of reality. Time literally passes more slowly for objects moving at high speeds relative to stationary observers. Space would contract along the direction of travel. Distances in the direction of motion would physically shrink from the perspective of the travellers. The journey that takes 2.5 million years from an outside perspective might feel much shorter to those aboard the ship, compressed by the relativistic effects of their enormous velocity. This phenomenon, called time dilation, emerges directly from Einstein's theory of relativity, from equations written over a century ago but confirmed by countless experiments and observations since. The faster you travel through space, the slower you move through time. This is not just theory anymore. We have measured it precisely. We have sent atomic clocks on high-speed jets and found that they tick slightly slower than identical clocks on the ground. We have observed particles created in particle accelerators living longer than they should because their internal clocks slow down at high velocities. GPS satellites orbiting Earth must account for both special and general relativistic time dilation effects. The satellites move fast enough relative to Earth's surface that time slows down for them compared to clocks on the ground, but they also orbit in weaker gravity than we experience at Earth's surface, which causes time to speed up for them compared to us. The two effects work in opposite directions, and both must be precisely calculated and corrected for GPS to work accurately. Without these relativistic corrections, GPS navigation would drift by miles within hours. At speeds approaching light speed, this effect becomes dramatic, transformative. Travellers aboard a ship moving at 99% light speed would experience time passing perhaps 7 times slower than observers on Earth. Their subjective journey time, the time measured by clocks on their ship and by the aging of their bodies, might compress to several 100,000 years instead of millions. Still an incomprehensibly long time, still far longer than human civilization has existed, but shorter than the outside perspective. At 99.9% of light speed, time dilation becomes even more extreme. Travellers might experience only about 50,000 years of subjective time during a journey that takes 2.5 million years from Earth's perspective. At 99.99% of light speed, the factor increases further. You could, in principle, make the subjective journey time almost arbitrarily short by getting closer and closer to light speed, approaching but never quite reaching that ultimate velocity limit. But here we encounter the first profound barrier, the first point where the physics of the situation creates problems that cannot be solved by any amount of engineering or determination. Time dilation helps the travellers, makes their subjective journey shorter, but it does nothing for the people waiting at home. Nothing at all. From Earth's perspective, the ship still takes 2.5 million years to reach Andromeda. The calendar on Earth continues ticking forward at its normal rate. Everyone you ever knew would be dead within decades of your departure. Your children would age and die. Your grandchildren would live their complete lives and pass away. Your entire family line would extend for thousands of generations and likely go extinct before your ship travelled even a fraction of the distance. Your civilization, the culture you came from, the language you speak, the values you hold, would transform beyond recognition or vanish entirely. Your species might evolve into something new, or cease to exist. The very continents would rearrange themselves. Plate tectonics would carry land masses thousands of miles from their current positions. Mountain ranges would rise and erode. Oceans would open and close. The night sky itself would look different as stars moved in their long orbits around the galactic center. New stars would be born from collapsing gas clouds. Old stars would explode as supernovae, scattering heavy elements into space. The galaxy would slowly rotate, its spiral arms shifting and reforming over millions of years. Antarctica might drift north and collide with Australia. Africa might split along the East African Rift Valley, creating a new ocean. The Atlantic Ocean, currently growing wider as the Americas drift away from Europe and Africa, might reverse direction and begin closing again. The Mediterranean Sea, once a vast ocean called Tethys, might vanish entirely as Africa collides more forcefully with Europe. The Himalayan mountains, currently the tallest on Earth, might erode down to mere hills while new mountain ranges rise elsewhere. When your ship reaches Andromeda, if it reaches Andromeda, if nothing goes wrong during the millions of years of travel, there would be no one left on Earth who remembers why you were sent. No one who cares about your mission. No one waiting for your signal or hoping for your return. The Earth itself might be unrecognizable, might be an airless rock if the sun has entered its red giant phase, might be completely destroyed if some cosmic catastrophe struck in your absence. This creates a fundamental disconnect in meaning that cannot be bridged by any technology. The journey becomes pointless from a human perspective because the humans who conceived it, funded it, built the ship, and launched it will all be gone millions of years before any information returns. The trip transforms into a one-way voyage not just through space, but through time, carrying travelers so far into the future that they become permanently separated from everything they knew, everyone they loved, every reason they had for beginning the journey in the first place. And time dilation only works, only provides this subjective shortening of the journey if you can actually reach these incredible speeds. This is not a small detail. Accelerating even a small spacecraft to 99% of light speed requires energy outputs that dwarf anything humanity has ever produced, energy outputs that dwarf the total energy production of our entire civilization over its complete history. The fastest human-made object ever created, the Parker Solar Probe, a small spacecraft designed to study the Sun's corona, reaches speeds of roughly 430,000 miles per hour as it swoops close to the Sun and uses solar gravity to accelerate. This sounds impressive. It is the fastest thing humans have ever built, and yet it represents only 0.06% of light speed, only 0.06%. The probe is barely moving by cosmic standards. For perspective, a rifle bullet typically travels about 2,000 miles per hour. A fighter jet might reach 1,500 miles per hour. The space shuttle in low Earth orbit travelled about 17,000 miles per hour. The Parker Solar Probe at 430,000 miles per hour moves roughly 25 times faster than the space shuttle. It is extraordinarily fast by any human standard. And yet light speed, at 670 million miles per hour, remains more than 1,000 times faster still. The gap between our fastest spacecraft and light speed is like the gap between a crawling baby and a supersonic jet. Reaching even 1% of light speed would require 1,000,000 times more energy than we used to launch that probe. 1,000,000 times. Not 10 times or 100 times, but 1,000,000. And the energy requirements grow exponentially as you approach light speed. Each additional increment of speed demands vastly more energy than the last. The physics creates a cost curve that rapidly becomes prohibitive, that rises so steeply it might as well be a vertical wall. Moving from 1% of light speed to 2% requires much more than twice the energy. Moving from 10% to 20% requires much more than twice again. The curve accelerates. As you approach the speed of light, the energy required approaches infinity. You can never quite reach light speed if you have mass, because reaching it would require infinite energy, and infinite energy does not exist. Let us try to visualize these energy requirements more concretely, in terms that might make the scale of the problem more apparent. Imagine a spacecraft with a mass of 1,000 tons, roughly the mass of a fully loaded commercial airliner, the kind you might see at an airport every day. This is not a particularly large spacecraft by the standards of science fiction. It is small, really, barely large enough to carry a small crew and their supplies for even a modest journey. To accelerate this ship to just 10% of light speed would require approximately 90,000 trillion megajoules of energy. Let me give you a comparison that might help. The total global energy consumption for an entire year, all the electricity, all the gasoline, all the coal and natural gas and nuclear power and renewable energy sources combined, equals roughly 600,000 trillion megajoules. Accelerating a single relatively small spacecraft to 1/10 of light speed would require about 15% of the total energy humanity produces in a year. Think about what that means practically. Every power plant on Earth, every solar panel, every wind turbine, every coal fire, every nuclear reactor, all of them working together, could produce just barely enough energy to accelerate 6 or 7 small ships to this velocity in a single year. And that is assuming we could capture and store and transfer all that energy perfectly, which we absolutely cannot. Current battery technology could not even begin to store such quantities of energy. The best lithium-ion batteries store about 1 megajoule per kilogram. To store 90,000 trillion megajoules would require 90 trillion kilograms of batteries. That is 90 billion tons, roughly 1,000 times more mass than the spacecraft itself. You would need batteries weighing 1,000,000 times more than your ship just to store enough energy to accelerate it, which makes the entire concept absurd. You cannot carry fuel that weighs 1,000,000 times more than your vehicle. And that calculation assumes perfect efficiency, an ideal scenario where every unit of energy input translates directly into kinetic energy of the spacecraft. In reality, no propulsion system achieves perfect efficiency. All real engines waste significant energy. Energy escapes as heat, radiates away as light, gets lost in vibration and noise and other forms that do not contribute to forward motion. A realistic propulsion system might achieve only 10% efficiency if we are very lucky and very clever. That multiplies the required energy by a factor of 10. Suddenly we are not talking about 15% of global yearly energy production, but 150%. We are talking about more energy than humanity produces in a year just to accelerate one small ship to 1/10 of light speed. And at that velocity, the journey would still take 25 million years. Now consider that 10% of light speed is nowhere near fast enough for any practical purpose. At that velocity, the journey to Andromeda would still take longer than the entire history of human evolution. To make the journey even remotely thinkable, you would need to reach significant fractions of light speed, 50% or more, ideally much more. But the energy requirements increase with the square of velocity. This is a fundamental principle of physics, derived from basic equations you could learn in an introductory course. Doubling your speed requires 4 times more energy. Tripling your speed requires 9 times more energy. Reaching 50% of light speed would demand energy inputs measured not in percentages of global yearly production, but in multiples of it. Multiple years of total global energy output, possibly decades or centuries, all devoted to accelerating a single spacecraft. And we would need to somehow collect this energy, store it, and transfer it to the ship in a controlled manner that does not vaporize the vessel or everyone aboard it. The Kardashev scale, proposed by Soviet astronomer Nikolai Kardashev in the 1960s, categorizes civilizations by their energy usage. It provides a framework for thinking about the development of technological societies and their energy needs. A Type 1 civilization can harness all the energy available on its home planet. All the solar energy striking the planet's surface, all the geothermal energy from its interior, all the wind and wave energy, all the fossil fuel reserves, everything. A Type 2 civilization can capture the total energy output of its star, presumably using some kind of massive structure that surrounds the star and collects its light. A Type 3 civilization controls the energy of its entire galaxy, collecting and using the energy from billions of stars spread across thousands of light years. These categories increase exponentially. Each step up represents roughly 10 billion times more energy than the previous step. By these standards, humanity currently ranks at approximately 0.7 on the scale. We are not even a Type 1 civilization yet. We cannot even fully utilize the energy resources of our own planet. We use only a fraction of the solar energy striking Earth. We have only scratched the surface of our geothermal reserves. Building a spacecraft capable of reaching Andromeda at speeds that would make the journey survivable, or at least reduce it to timescales that some form of human society might maintain, would require energy resources characteristic of a Type 2 civilization at minimum. We would need to capture and store the entire energy output of the Sun, not just the tiny fraction that strikes Earth, but the total output radiating in all directions into space. Most of the Sun's energy misses Earth entirely, shooting off into the void where it serves no purpose. This would involve constructing something like a Dyson sphere, a theoretical megastructure first proposed by physicist Freeman Dyson. Imagine a spherical shell surrounding the Sun completely, at a distance of roughly 93 million miles, the current distance from Sun to Earth. This shell would collect all the sunlight radiating outward, converting it to electricity or some other useful form of energy. The structure would have a surface area billions of times larger than Earth's surface. Current human technology cannot build anything remotely approaching a Dyson sphere. The engineering challenges involve scales beyond our current capabilities by factors of millions or billions. We would need to disassemble entire planets to obtain sufficient building materials. Mercury alone might not provide enough metal and minerals. We might need to take apart several planets, perhaps all the rocky planets in the inner solar system. We would need to manufacture structures larger than Earth's orbit, maintaining them somehow against the intense radiation, gravity, and space environment surrounding a star. We would need to develop materials strong enough to withstand the stresses involved, light enough to be practical at such scales, and stable enough to last for centuries or millennia without constant maintenance. We would need power systems to position the components, to adjust their orbits, to prevent the structure from falling into the Sun or drifting away into deep space. The project would take thousands of years, employ billions of people, and consume resources we can barely imagine. And even then, even if we built this impossible structure, we would have just barely enough energy to launch ships to Andromeda at velocities that make the journey survivable on evolutionary timescales. Even if we somehow solved the energy problem, solved it completely with some breakthrough we cannot currently foresee, and built a ship capable of reaching significant fractions of light speed, we would immediately encounter another barrier. This one comes not from our own limitations, but from the nature of space itself. Space between stars is not truly empty. It contains matter, thin but not entirely absent. The interstellar medium, as astronomers call it, consists of roughly 1 hydrogen atom per cubic centimetre. This sounds negligible. It sounds like nothing. 1 atom in a space the size of a sugar cube? That might as well be vacuum, right? But at relativistic speeds, even this thin gas becomes a serious problem, potentially a deadly one. When you travel at 99% of light speed, every hydrogen atom you encounter impacts your ship with kinetic energy equivalent to a high-energy cosmic ray. These are not gentle collisions. Each impact delivers enormous energy, concentrated in a tiny area. The faster you travel, the more energetic these impacts become. The relationship is not linear but exponential. At sufficiently high speeds, the interstellar medium transforms from a gentle breeze you barely notice into a deadly radiation storm, an endless bombardment of high-energy particles. Your spacecraft would be bombarded continuously by particles, millions or billions of impacts per second depending on your cross-sectional area and velocity. High-energy particles would erode its hull, slowly eating away at whatever material you used for construction. They would damage its systems, causing electronics to fail, computers to malfunction, sensors to give false readings. They would deliver lethal radiation doses to any biological crew, even through heavy shielding. The erosion problem alone might be insurmountable. Even the hardest materials we know, substances like diamond or tungsten carbide, would gradually wear away under continuous bombardment. The front surface of the ship would be sanded down atom by atom, layer by layer, as hydrogen atoms strike at relativistic velocities. Over thousands or millions of years of travel, this erosion could significantly damage or destroy the spacecraft's structure. This effect places practical limits on how fast you can actually travel through interstellar space, even if you solve the energy problem. Engineers who have studied this problem estimate that spacecraft traveling faster than about 50% of light speed would need such massive shielding to protect against interstellar medium impacts that the weight of the shielding would make the journey impractical. The faster you want to go, the more shielding you need, which increases your mass, which requires more energy to accelerate, which requires more fuel, which increases your mass further. This creates a vicious cycle where every attempt to solve one problem makes another problem worse. The engineering challenges multiply and interact until they become insurmountable not just practically, but theoretically. You reach a point where no clever engineering can resolve the fundamental contradictions. The physics itself prevents the journey from working, but perhaps the most disturbing barrier has nothing to do with engineering or energy or shielding. It emerges from the nature of the universe itself, from a property of space that makes most of the cosmos permanently unreachable, regardless of what technology we develop, regardless of how much energy we gather, regardless of how clever we become. The universe is expanding. This is not a theory or speculation, but an observed fact, confirmed by decades of careful measurements and observations. Space itself grows larger as time passes, and this expansion carries distant galaxies away from us. Astronomers discovered this expansion in the 1920s when Edwin Hubble observed that nearly all galaxies show redshift in their spectra, indicating they move away from us. More surprisingly, he found that more distant galaxies recede faster than nearby ones. The redshift occurs because light stretches as the space it travels through expands. Light from receding galaxies gets stretched to longer wavelengths, shifting it toward the red end of the spectrum. By measuring this redshift precisely, astronomers can calculate how fast galaxies are receding. By measuring their distances through other methods, they can map the relationship between distance and recession velocity. This relationship, now called Hubble's law, reveals that space expands uniformly in all directions. Galaxies do not move through space away from us. This is a common misunderstanding, but an important one to correct. They are not traveling like ships through an ocean. Rather, the space between galaxies grows, carrying them apart like raisins in rising bread dough. If you make bread dough with raisins mixed throughout, then set it aside to rise, the raisins move farther apart as the dough expands. As the dough expands, raisins embedded in it move farther apart, not because they travel through the dough, but because the dough itself grows. They remain stationary relative to the dough immediately around them, but their separation increases as more dough fills the space between them. This is how cosmic expansion works. Galaxies remain more or less stationary relative to the space immediately around them, but the amount of space between galaxies increases continuously. This expansion creates consequences for interstellar travel that many people find difficult to accept or understand. When space expands, distances grow. The gap between us and Andromeda increases over time, at least in most contexts. Currently, Andromeda actually moves toward us at about 70 miles per second because local gravitational attraction overcomes cosmic expansion on these relatively small scales. The Milky Way and Andromeda orbit each other in a gravitationally bound system, a local group of galaxies held together by mutual gravity that will eventually merge the two galaxies. But this represents a special case, a lucky circumstance. Most galaxies beyond our local group recede from us due to cosmic expansion. They move away, their distances increase, and they will never get closer again. For sufficiently distant galaxies, space expands between us faster than light could travel through that space. And here is where it gets disturbing. This might seem to violate the speed of light limit, but it does not. Special relativity forbids objects from moving through space faster than light. Nothing with mass can accelerate to light speed, and nothing can transmit information faster than light. But special relativity places no limits on how fast space itself can expand. Space is not an object. It is not matter or energy. It is the stage on which matter and energy exist, the coordinate system we use to describe where things are. And that stage can grow as fast as it wants. There is no speed limit on the expansion of space itself. This creates what astronomers call the cosmological event horizon, a boundary in space beyond which we can never reach, regardless of technology or effort. Galaxies beyond a certain distance, currently estimated at about 16 billion light-years away, recede from us faster than light can travel. We can see them now because the light currently reaching us was emitted billions of years ago when they were closer, when space between us was smaller. But we can never reach them. No matter what technology we develop, no matter how fast we travel, no matter how much energy we collect, because the space between us grows faster than we could ever cross it. Even traveling at exactly the speed of light, taking a magic photon express that could carry human consciousness at the maximum possible velocity, we could never close the distance to these galaxies. We would be like runners on an expanding treadmill, moving forward at maximum speed but falling farther behind because the treadmill stretches faster than we can run. We could run forever, expending infinite energy, and still never reach the end. The destination recedes faster than we approach. Andromeda lies well within the range where travel remains theoretically possible. It belongs to our local cluster of galaxies, bound by mutual gravity, approaching rather than receding. If the universe never expanded at all, if space were static, Andromeda would still be incredibly difficult to reach, but at least it would not be getting farther away. But the expansion of space still matters for Andromeda in another way, a more subtle but equally important way. It reveals that the window for intergalactic travel, even just between the closest galaxies, will not remain open forever. As the universe ages and expansion continues, as dark energy drives galaxies apart at ever-increasing rates, fewer and fewer galaxies will remain reachable even in principle. The cosmic horizon will shrink. In the deep cosmic future, perhaps 100 billion years from now, galaxies beyond our local group will have receded so far that their light will no longer reach us. They will pass beyond the cosmological event horizon, beyond the distance where their light can ever catch up with the expanding space. Future astronomers, living 100 billion years from now, will observe a universe containing only the merged remnant of the Milky Way and Andromeda, a single massive elliptical galaxy surrounded by empty darkness. They will look out and see nothing else. No distant galaxies, no cosmic web of galaxy clusters, no evidence that billions of other galaxies once filled the observable universe. They will have no way to discover the Big Bang Theory because the redshift evidence will be gone. They might conclude they live in a static, eternal universe consisting of just their own galaxy surrounded by infinite void. This adds temporal urgency to the impossibility of our situation, a time limit to our cosmic imprisonment. Not only can we not reach Andromeda now, not only is the journey impossible given our current limitations, but the universe operates on timescales where even the possibility of such journeys may eventually vanish completely. The window is closing, albeit very slowly. The cosmos is isolating each island of galaxies more completely with each passing eon. Even if we somehow solved every engineering challenge, somehow gathered the necessary energy, developed the required technology, built the ships, and launched a mission to Andromeda, we would still face barriers that have nothing to do with physics or engineering and everything to do with human biology and psychology. These might be the most insurmountable barriers of all, because they emerge from what we are rather than what we know or what we can build. Consider the duration of the journey. Even travelling at 10% of light speed, which would represent a technological miracle beyond anything we can currently imagine, a velocity that would seem like magic to anyone living today, the trip would take 25 million years. Think about that number in terms of human timescales. The human species, Homo sapiens, has existed for only about 300,000 years. That is how long anatomically modern humans have walked the Earth. Recorded human history, the period for which we have written records and archaeological evidence, spans roughly 5,000 years. The longest continuously maintained human institution, perhaps the Catholic Church or possibly some Eastern religious traditions, has endured for about 2,000 years. Even these ancient institutions have changed dramatically over time, reinterpreting their missions, adapting to new circumstances, barely recognizable to their founders. We have no examples of human societies, organizations, or projects maintaining continuity and purpose for even 10,000 years, let alone millions. Nothing humans have ever built has lasted even 1/100% of the time required for this journey. The United States, one of the world's most powerful nations, is less than 300 years old. Most corporations, even the largest and most successful ones, exist for decades, not centuries. Very few companies survive more than 100 years without radical transformation or dissolution. Families maintain cohesion for generations, perhaps 5 or 10 generations in exceptional cases, not millennia. The idea that humans could maintain a focused purpose across millions of years contradicts everything we know about how human societies actually function. A generation ship traveling to Andromeda would need to sustain not just individual human lives, but entire civilizations, for periods exceeding all of recorded history by factors of thousands. The ship would become its own world, its own society, developing its own culture, politics, conflicts, and possibly its own reasons to abandon or redirect the original mission. It would be a world unto itself, isolated from Earth and from its destination, existing in a strange liminal state between departure and arrival for timescales that dwarf all human experience. After a few thousand generations, perhaps after even a few hundred generations, would the descendants even remember Earth? Would they know where they came from? Would they care about the mission their ancestors began millions of years ago? About goals set by people so remote they might as well be mythological figures? Would they maintain the ship systems required to complete a journey whose purpose had long since lost relevance to their lives? Human psychology compounds these problems in ways that might be insoluble. We struggle to plan beyond our own lifetimes. Most of us have difficulty thinking even that far ahead. Politicians rarely think past the next election, which might be 2 or 4 or 6 years away, depending on the system. Corporate leaders focus on quarterly earnings, on stock prices that change daily, on market trends that shift monthly. Even the most long-term human thinking typically extends only to our grandchildren or perhaps great-grandchildren. We might plant trees that will mature after we die. We might save money for descendants we will never meet. But even these relatively long-term actions only span decades. The cognitive machinery that motivates human behavior operates on timescales of days, months, years, perhaps decades at most. We possess no mental framework for conceptualizing purposes that extend across millions of years, no emotional connection to outcomes so far removed from our existence. Our brains simply did not evolve with this capability because it never mattered for survival or reproduction. Evolutionary psychology explains why this limitation exists. Our ancestors needed to solve immediate problems, finding food today or this week, avoiding predators now, raising children over a span of years, forming alliances that might last decades. Natural selection optimized human cognition for short-term planning within small social groups, for understanding causes and effects that occurred within lifetimes, for caring about outcomes we might personally witness. We evolved to care intensely about people we know personally, about family and friends and tribe members. We struggle with abstractions about distant times and faraway places. We intellectually understand that future generations will exist, but we do not feel emotional connection to them in the same way we feel connected to people we know. This is not a moral failing, just a feature of how our minds work, shaped by millions of years of evolution that never needed to optimize for thinking about timescales of millions of years. This creates a fundamental mismatch between the human cognitive toolkit and the requirements of intergalactic travel. We can intellectually understand that a journey might take millions of years. We can write the equations, calculate the distances, draw up the plans, but we cannot make ourselves care about outcomes so far removed from our own experience in the visceral way that motivates action. The emotional and motivational systems that drive human behavior simply do not engage with such timescales. They were not designed to, and there is no obvious way to redesign them. Generation ships would also face the challenge of maintaining genetic diversity over thousands of generations. A viable human population requires thousands of individuals to avoid inbreeding and genetic drift. Population geneticists have calculated minimum viable populations for various species, and for humans, the number is probably somewhere between 5,000 and 10,000 individuals. Any smaller and genetic diversity drops too low, inbreeding becomes unavoidable, and the population eventually collapses from accumulating harmful mutations. But maintaining thousands of people on a spacecraft for millions of years demands enormous resources. Food production facilities large enough to feed thousands of people indefinitely. Water recycling systems that can purify and recycle every drop for millions of years without loss. Atmosphere regeneration equipment that can produce oxygen and remove carbon dioxide at sufficient rates. Living space large enough that people do not go insane from crowding, along with all the social infrastructure that implies. Schools, hospitals, places of work, places of recreation, places for all the activities that make human life bearable. All of this scaled up to support a complete isolated civilization, hermetically sealed inside a spacecraft traveling through absolute void. The ship would need to be entirely self-sufficient for periods longer than human civilization has existed. Any critical system failure would be catastrophic, would potentially doom everyone aboard. If the water recycling system degraded over time and efficiency dropped even slightly, people would slowly die of thirst. If the agricultural facilities failed, if disease struck the crops, or some system malfunction destroyed food production, people would starve. If radiation shielding eroded over millennia of exposure to cosmic rays and interstellar radiation, cancer rates would rise until the population collapsed. There would be no help, no rescue, no possibility of obtaining replacement parts or outside assistance, no supply ships coming from Earth, because Earth would have forgotten you long ago. No radio contact, because even at light speed messages would take millions of years to reach home, and millions more for any reply. The void between galaxies offers nothing that could sustain human life. No resources to extract, no materials to use for repairs. You would be completely isolated, absolutely alone, dependent entirely on the systems you brought with you. Biological challenges multiply over such timescales in ways we cannot fully predict or prevent. Radiation exposure in deep space increases cancer risk and causes genetic mutations. Even with shielding, even with the best protection we can design, cosmic rays would slowly damage DNA in the population. Some fraction of cosmic rays, the highest energy ones, would penetrate any shielding we could practically construct. Over thousands of generations, accumulated mutations might significantly alter the human genome. The descendants who arrived at Andromeda might be genetically distinct from the humans who departed Earth, evolved or drifted into a form we might not recognize as fully human. They might be unable to interbreed with the original Earth population, separated by millions of years of genetic divergence. They might have evolved resistance to certain types of radiation damage, but lost other capabilities in the process. Evolution does not stop just because you are on a spaceship. It continues operating on any population that reproduces across many generations. Psychological effects of confinement would create additional problems that we can barely begin to predict. Humans evolved for life in open environments, with natural landscapes, varied weather patterns, and complex ecosystems. We developed for a world of horizon and sky, of seasons and storms, of forests and plains and oceans. Our psychology adapted to that world, expects that world, needs that world in ways we are only beginning to understand. Confining thousands of people inside a spacecraft for their entire lives, generation after generation, for millions of years, would create profound psychological stresses we cannot fully predict. We have some data from extreme environments on Earth. Antarctic research stations, submarines, space stations, isolated communities. Studies of these groups show that even short periods of confinement cause significant psychological effects. People become irritable, depressed, anxious. Social conflicts arise more easily. Mental health problems increase. And these studies cover months, or at most a few years, not millions of years and thousands of generations. Extrapolating these effects across millions of years and countless generations suggests deep problems we lack the tools to solve. You cannot simply scale up from a year to a million years. New problems emerge at longer timescales. Social structures might ossify or collapse. Culture might stagnate without outside input or transform in ways that undermine the mission. Mental illness might become endemic. Motivation to continue the journey might simply evaporate after enough generations pass that the original purpose becomes meaningless. Some futurists propose that we might solve the biological problems through technology. Perhaps instead of sending humans in our current form, we send artificial intelligence. Perhaps we upload human consciousness into digital form, converting biological minds into patterns of information stored in computers, allowing us to travel as data rather than fragile biological organisms. Perhaps we send frozen embryos to be raised by robots upon arrival, eliminating the need to keep thousands of people alive during the journey. Perhaps we use genetic engineering to modify humans into something post-human, beings with extended lifespans and enhanced resilience to space travel and radiation exposure. But these suggestions, while technically interesting, only deepen the problem they attempt to solve. They do not resolve the fundamental issues, but rather transform them into different, arguably worse versions. If we send artificial intelligence instead of humans, then humans do not reach Andromeda. The mission succeeds in a technical sense, but humanity gains nothing from it, except perhaps information transmitted back across millions of years, data that might arrive long after humans have gone extinct. If we upload consciousness into computers, transforming minds into software running on hardware, are the uploads still human in any meaningful sense? They might retain memories of being human, might think they are human, but they would lack bodies, lack biological drives, lack the embodied experience that arguably makes us what we are. The uploaded mind would be an information pattern, ones and zeros in computer memory, fundamentally different from biological consciousness in ways we do not fully understand. If we genetically modify ourselves into post-human beings, engineering our DNA to create something more suited to space travel, do we retain continuity with our origins? At what point do modifications become so extensive that the result is no longer human but something else entirely? This question has no clear answer, but it matters profoundly because it determines whether the journey represents human achievement or the replacement of humanity with something else. Consider a mission that successfully sends a spacecraft to Andromeda carrying artificial intelligence or uploaded human consciousness or genetically engineered posthumans. What exactly has been accomplished? Not the satisfaction of human curiosity in any direct sense, because no current human will ever learn what was found. Not the expansion of human civilization, because what arrives at Andromeda will be so changed from what departed Earth that calling it human becomes questionable at best. Not the preservation of humanity, because the beings that arrive will have diverged beyond recognition from their ancestors. They might carry human DNA, or human memories, or human knowledge, but they will not be human in the sense we understand the term today. They will be our descendants, perhaps, but not us. As different from current humans as we are from the first single-celled organisms, separated by a gulf of time and change that makes comparison almost meaningless. The journey to Andromeda, if somehow achieved through technologies we cannot imagine and with resources we cannot produce, would only be meaningful to beings so transformed from current humans that they might as well be alien species. The mission might continue from pure momentum, a tradition maintained for millions of years without any living memory of why it started. Imagine a vast ship travelling through the void, generation after generation born, living, and dying in its corridors, maintaining systems they no longer understand, pursuing a mission whose purpose has been forgotten, a ritual performed by creatures who have no understanding of its original intent or meaning. This disconnection reveals something important about human ambition and cosmic reality, something we need to confront honestly rather than hiding behind technological optimism. Our dreams of reaching the stars emerge from a species whose complete existence spans barely 300,000 years. We are infants by cosmic standards, barely self-aware, just beginning to look around and understand where we are. We imagine ourselves crossing millions of light years, while our recorded history covers only 5,000 years, a blink of an eye by the standards of galactic time. We think in generations, planning decades ahead at most, while the cosmos thinks in ages that span millions or billions of years. We plan in decades, maybe centuries, for the most ambitious projects, while the journey demands millions of years of continuous, directed effort. The mismatch between human timescales and cosmic requirements is not a gap to be bridged with clever engineering, but a chasm that grows deeper with every layer of analysis. The more carefully we examine what intergalactic travel would actually require, the more impossible it becomes. Not just technologically impossible, meaning we lack the tools but might build them someday. Conceptually impossible, meaning the very concept of the journey contradicts what we know about human nature and physical law. We lack the mental framework to meaningfully plan across such durations. We lack the social capability to maintain purpose across such time spans. We lack the biological continuity to remain ourselves across such journeys. Yet even considering these barriers serves a purpose beyond simply listing obstacles or cataloguing our limitations. Understanding why we cannot reach Andromeda reveals truths about our cosmic situation that inform how we might think about human existence and meaning in a universe far larger than we can ever explore. These truths might be uncomfortable, but discomfort is not the same as meaninglessness. The universe is not designed for travel. This statement might seem pessimistic, but it is simply an observation about the structure of reality. The enormous distances between galaxies, the cosmic speed limit built into space-time itself, the expanding space that carries destinations beyond reach, all suggest that cosmic geography keeps civilizations isolated by fundamental design. If design is even the right word for physics, operating as physics must operate, for mathematics working itself out in the structure of space and time, each galaxy represents an island in an infinite ocean. The physics of that ocean, the distances involved, the speed limits imposed, the expansion occurring, all prevent any voyage between islands within any reasonable time frame. We are stranded on our island, able to observe distant shores, but unable to reach them, separated by waters too deep and too wide for any vessel to cross. This isolation may explain the famous Fermi paradox, the apparent contradiction between the high probability of extraterrestrial intelligence and the complete absence of evidence for such intelligence. If life is common in the universe, if intelligence emerges readily from biological evolution, if technological civilizations arise frequently across billions of stars, then where is everyone? Why do we see no evidence of alien civilizations? No radio signals, no megastructures, no signs of galactic engineering projects? If every civilization faces the same insurmountable barriers to intergalactic travel that we face, then advanced species throughout the universe might exist in permanent isolation, unable to contact neighbors in other galaxies, unable to confirm whether others exist, unable to break the cosmic silence that surrounds every inhabited world. The universe might be filled with civilizations, all looking outward and wondering why they see nothing, all imprisoned by the same fundamental physics. The cosmos may be filled with intelligent life, Billions of civilizations might exist across the observable universe, each imprisoned within its own galaxy, contemplating the same stars we contemplate, wondering the same questions we wonder, facing the same insurmountable barriers we face. They look toward us across millions of light years, we look toward them, and the void between us ensures that we will never meet, never communicate, never confirm each other's existence. We are all alone together, countless islands of consciousness scattered across an ocean too vast to cross. But there is another way to interpret these facts, a perspective that transforms cosmic imprisonment into cosmic meaning. This interpretation might not satisfy everyone, might not solve the emotional problem of isolation, but it offers a different lens through which to view our situation. The vastness that imprisons us is the same vastness that created us. The nuclear furnaces of stars forged the heavy elements in our bodies, the carbon and nitrogen and oxygen and iron that make biological life possible. Those elements only exist because stars burned for billions of years, fusing lighter elements into heavier ones, then exploding to scatter those elements through space. The cosmic distances that separate galaxies allowed the billions of years necessary for biological evolution. If the universe were smaller, if galaxies were closer together, gravitational interactions would have disrupted star formation and planetary stability long before life could emerge. The same physics that prevents our escape also enables our existence. The prison walls are load-bearing structures. Remove them and the prison collapses, taking us with it. We are not external to the cosmos, trapped within it against our will. We are expressions of the cosmos, matter configured into patterns capable of contemplating matter, arrangements of atoms that can think about atoms. We cannot reach Andromeda in any physical sense, but we can see it. We can measure its distance with extraordinary precision, using stellar parallax and variable stars and other astronomical techniques. We can calculate its composition from the spectrum of its light, reading the absorption lines that reveal which elements exist in its stars. We can predict its collision with our galaxy 4 billion years from now, when these two spiral systems will merge into a single massive elliptical galaxy. We can understand why we cannot reach it physically, which is itself a form of reaching. Understanding transcends physical presence in some ways. To know something deeply, to comprehend its nature and its relationship to yourself, might matter more than touching it. The light from Andromeda that entered your eyes tonight carried information across 2.5 million years of void. Those ancient photons, created in the atmospheres of stars when Earth was young and humans did not exist, became electrical signals in your retina. They triggered chemical reactions in photoreceptor cells, generating nerve impulses that traveled along your optic nerve. Those impulses became patterns of neural activity in your visual cortex, then higher-level representations in your brain, and finally, conscious experience of a distant galaxy. In that moment of observation, Andromeda was no longer entirely separate from Earth. It had become part of your mind, part of human knowledge, part of the cosmic story we are learning to tell. The photons that left Andromeda 2.5 million years ago completed their journey in your consciousness. You are where they were going all along, the endpoint of their vast journey, the meaning of their motion through the void. We may be prisoners of physics, confined to our local cosmic neighborhood for all of human existence, possibly forever, but we are prisoners who can see the entire prison. We are prisoners who can understand the walls that contain us, who can measure them and calculate their properties and comprehend why they exist. We are prisoners who can appreciate the vastness we can never traverse, who can feel wonder at scales beyond our reach. Perhaps consciousness, observing the universe, understanding the universe, appreciating the universe, serves a purpose that transcends physical travel. Perhaps knowing is its own form of reaching, more profound in some ways than physical presence. The eye and the mind can go where the body cannot. The imagination can visit places the spacecraft will never reach. Andromeda hangs in the autumn sky tonight, 2.5 million light-years away, approaching very slowly, but forever unreachable by human travelers. 1 trillion stars burn in its spiral arms, each one a sun, many of them with planetary systems. Billions of planets orbit those stars, worlds we will never visit, landscapes we will never see. Perhaps some of those worlds harbour conscious beings like us, or unlike us. Beings who look toward our galaxy and wonder the same things we wonder, who feel the same cosmic loneliness we feel, who face the same insurmountable barriers we face. We will never meet them, can never meet them. The physics forbids it, the distances prevent it, the timescales defeat it. But we can know they might exist. We can imagine their thoughts, wonder about their lives, recognize our shared situation. We can recognize that consciousness, wherever it arises in this vast universe, faces the same cosmic constraints that imprison us all. The real reason we cannot reach Andromeda is not a single barrier, not one problem that might be solved with enough cleverness or effort. It is an interlocking system of physical constraints that apply uniformly throughout the cosmos. Distance creates journey times exceeding any conceivable human duration. The speed of light prevents shortcuts that would compress these journeys. Cosmic expansion carries most of the universe beyond any possible reach. Human biology, psychology, and institutional memory cannot span the timescales involved. These barriers are not defects in the universe, not bugs in the cosmic code that might be patched. They are the universe. The same physical laws that create galaxies, ignite stars, and enable life also separate those galaxies by insurmountable voids. We exist because physics operates as it does. Our confinement is not an unfortunate side effect, but a necessary consequence. Our confinement is the price we pay for existence itself. Look toward Andromeda tonight if the sky is clear where you are. Find a dark spot away from city lights if you can. Let your eyes adjust to the darkness. See the light that departed when your ancestors were learning to make tools, when humans were still figuring out how to survive on the African plains. Contemplate the trillion stars you will never visit, each one perhaps attended by worlds you will never explore. Think about the possible civilizations you will never contact, beings who might be looking back toward us at this same moment across the unbridgeable gulf. Feel the cosmic loneliness of existence, isolated by incomprehensible distances, by physics that builds walls we cannot climb, by mathematics that forbids the journeys we dream about. Let yourself feel small, insignificant, lost in a universe too vast to ever know completely. This feeling is appropriate, is honest, is true to the facts of our situation. Then recognize the miracle of your awareness, the strangeness of your existence. You are matter configured into patterns capable of contemplating its own imprisonment. You are physics that not only builds walls but builds consciousness to recognize those walls. You are part of a universe that creates beings who can understand why they can never escape, who can look at their prison and comprehend its structure. The galaxy that cannot be reached remains the galaxy that can be known, and perhaps knowing is the only form of reaching that the universe permits, the only connection possible across these impossible distances. Perhaps this is enough, or has to be enough, because it is all we have. The light continues arriving, carrying information across the void. We continue observing, learning, understanding. The universe knows itself through us, sees itself through our eyes, contemplates its own vastness through our consciousness. And in that contemplation, in that knowing, perhaps we find the meaning that physical travel could never provide.